So, my primary job will be to keep all of you engaged, because you've had lunch, you had 2 cups of coffee, and there's a lot of information that came your way, right? Each one of them is can occupy a day in itself. Choosing the right DB, the axis of variation, event-driven architecture, each of them are like, people do 2-day conferences on that. So think of my talk as like a homework, you take it home. And it's a bit of a case study too, because there will be a little bit of talk about general architectural principles and how do we use it at Suki, but it's more focused on a specific problem that we try to solve. And what are the challenges we faced and the approaches we took? It's not, you should think of this as how we approached the problem solving from architectural perspective and draw your insights and lessons from it, right? So I try to be, as communicative and as responsive as possible, so that we stay engaged, right? So now, first thing, you don't do architecture without understanding what you are architecting, right? Because you have better things to do. So let's understand the problem domain in which Suki was architected, right? And we will focus. Suki as a product has components, but the one that I'm going to talk about is voice agent. It's the most complex component of ours. But there are other problems which have separate architectures that I'm not talking about today. So it's not just the voice agent that we solve. That's one of the most important pieces of the puzzle. So, and the story starts in US healthcare setting, right? US healthcare market is very vast, right? Trillions of dollars, you can't imagine, right? And you have at the center is the doctor-patient conversation. Patients coming in to visit doctors, doctor treating them, and hopefully they get better. And then this happens in 2 kinds of settings. If you're a doctor, you're either practicing independently, you're a physician, independent physician, or you are in a hospital setting, you are in an enterprise. Generally, this is there are hybrid settings also, but let's keep things simple, right? And then in US setting, you have something called as electronic health records. I'll keep referring to this as EHR, right? It's a big thing, it's a big concept in US, electronic health records. Recently, the government of India launched ABDM, Ayushman Bharat Digital Mission. Think of it as an EHR from the government. So here in India, the intention is to own the patient data by the government and it regulated. But in US, it's owned by enterprises, right? Some of the popular examples are Epic, Cerner, Athena. These are the enterprises which host patient data. So patient comes to the doctor, diagnosis happens, they make notes, they enter into the health record system. Not everybody uses health record system, but they want the benefits of digitization. So some of them just want digitized clinical notes, right? So it's called a COPE, computerized order entry by physician, but digitized clinical notes. Simple promise. This is where the problem happens. Now, as an architect, you don't immediately start to solve for this. You try to understand, is there a real problem actually, right? So you base your decisions on data. You're a hard-nosed scientist, right? So, and this is from CDC data, Center for Disease Control US, and the sources are here. So we see that 89.9% of physicians use EHR, electronic health record systems in US, right? So doctors are using EHR to make note entries about the patient. Your patient, you walk in, you have diabetes, whatever. I make a note about it, I save it, and that is the EHR. 89.9% use it. 66.6% of the doctors who use it are not satisfied with it. We'll see why, but they're not satisfied. And the breakdown is given below. 34% are somewhat satisfied, and so on and so forth. But even if you're somewhat satisfied, that you just, because there is an option somewhat satisfied, you say somewhat satisfied. It's not really serving your purpose, right? And if you see this chart, it says the average number of hours that a doctor spends just documenting, not treating patients, just documenting what they have done throughout the day outside of their work. So you're a doctor, you work 9 to 5, right? You go home and you spend, most of the doctors, let's say 40-50% of doctors spend 1 to 2 hours per day, 1 to 2 hours extra per day, just documenting, not treating, not prescribing medication, nothing. Okay? So that some spend even more, right? See, Suki AI office is at Kerala. My home is in Ara. It's 22 kilometers, right? There are two ways to reach the office. I can drive or I can take the metro. Metro saves me half an hour. Every single day I choose metro because it saves half an hour, right? Here we're talking about 2 hours per day per doctor extra. They're not doing the work that they're qualified for. They're just being data entry clerks. This is a problem, right? You are an architect, you see this, there is a problem. You can solve this, right? But, we live in the modern world. Not everybody is a hard-nosed data scientist. Some are just chill. So they want a tweet. So let's talk about this. So this is not an outrage tweet. This is not somebody sitting on their couch and writing on the Twitter because they have nothing better to do. This is by the doctor. And there is actually a movement called as fix EHR. That means EHR is causing problems to me. I'm burning out. I'm doing extra work that I'm not supposed to do. And fix it. And here is a doctor, covering all the problems that are generated due to EHRs. But let's think objectively. Let's find out what are the actual problems. Patient interaction is reduced. This is supposed to be the central thing of being a doctor. They become doctors not to earn money, not to, work outside office hours, but to treat patients. And that is just one step in this entire process. Look at the amount of documentation they are doing before and after this. So this is certainly a problem. EHR interaction is increased. A tool that is supposed to solve your problem is becoming your job. You're spending more time in front of the computer and the web portal, learning where to click, what shortcut to use, instead of talking to patient. This is the problem. Tool is supposed to solve the problem, not become a problem. Medical coding imposes cognitive burden. In US healthcare setting, there is a code for every disease and symptom. There is even a code for earthquake, right? Fire hazard. Everything has a code because you need it for insurance and for some other purposes, right? How can you remember all those codes? There are at least 90,000 codes in just one medical standard called as ICD-10. There are other standards also. Some have more than that. You can't remember all that. Somebody comes in and says they have diabetes with left leg pain. There is a unique code for that. How are you going to look that up? Not possible, right? Some doctors remember it, but not everybody is a hero like that. Writing full clinical note consumes time. So American notes are 4 times longer because of regulatory requirements. There's an online survey you can check about. Because they are thorough, but it takes more time, right? You are burning up. And there is no help. If you want all these things, you need some help. You need somebody to store those codes, map those codes. You need this EHR was supposed to solve these problems, but it's creating them. So this was the problem, right? You were an architect, you went into the market, you recognized a constituency which has a problem. Now you are going to go into a cave and you have come out with a solution, right? So it's built on these 5 principles, and this is directly derived from company's mission statement, right? So people say mission statement, but so I'm just trying to tell you how architectural choices are translated from a mission statement. Mission statement is not just a blob of text. You should take it and translate it into architectural choices. That's your job as an architect, right? So we want to solve this problem, very specific problem, documentation problem, with 5 pillars. The first is we want to be assistive. We want to help. Okay, EHR is a tool. It's not a problem. So we have to get rid of. We can't get rid of it. It's needed. It's regulated. You have to use it. We have to make it easy to use. So let's be assistive. Principle number 1, foundation of the whole thing. 2, it has to be invisible. You shouldn't be learning anything else. It should be intuitive to use, very easy. It doesn't interfere with you. You barely even realize it's there. That's why it's invisible. It's accurate. What if I build a product that is 50% accurate? Why will you use it? Granted, it's invisible and it's trying to help you, but it steps down all the time. No point, right? It has to be accurate. Real time. So you can potentially say, I will build a product, you give some input to it, it will come back to you 2 hours later. It's fine for some people, but not for many people, especially doctors, when they're dealing with patients, having a conversation, they want real-time feedback. Because it gives them a sense of what they have said, where is the diagnosis going, where should I correct, What should be done incrementally? It needs to be real time. Should be voice experience based. And this is a paradigm shift. This is a belief. You can say I will build a web portal, right? Fair enough. You can have all the 4 qualities. But the company and the founder, Puneet, he chose this paradigm. He said it's going to be voice driven because it's hands free. You don't have to sit and type. You don't have to click. You just talk to it. That's how modern applications are building, right? Very difficult to do in 2015. Now not so much, right? And we'll see why. Mission statement, pyramid of values, you saw. Now let's see what architectural choices you make and how are you restricted by that. You want a voice-based solution, there is a solution available, technology available, automatic speech recognition, ASR, right? And that's basically based on speech-to-text technology. So you are an architect, you're trying to architect a voice agent for doctors. You go out, okay, now you've realized I want 1, 2, 3, 4, 5. How can I solve 1? How can I solve 2? How can I solve 3? This is your journey into technology now, right? So you find out this is the one that's available now. Pretty much the only choice you have. Real time, you want a streaming data flow. You want sub-second end-to-end latency. You can always say I want millisecond latency, but that's not the use case here. I mean, here sub-second is good, right? So you can optimize it further, but anyway, this is what we want. And the choices for that are gRPC, protocols, WebSockets, protocol buffers, and caching. These are see, just realize, right? The choice of real time imposes architectural restrictions on what you can and what you can't use, right? This is the important bridge that you have to cross, right? And here is a lot of hard work that I'm not highlighting. You need to run benchmarks for these. You need to evaluate this. You need to find out use cases, how they will scale, what is the current concurrency, and etc. Lots of hard work goes in deciding on this, right? And this has been our journey. It has to be accurate, so you need best-in-class medical transcription. It's not easy. Anybody can translate a common English sentence from audio to text. But if you're saying something like, I'm prescribing metronidazole to the patient, they are supposed to consult for hypochondria. I mean, it's not easy to translate those sounds into text. You need a dedicated ASR for that. So you need specialized ASR. But at the same time, you want to be assistive through voice. So you need to understand common English stuff also. So there's a dual challenge you have to solve. So you need special purpose vehicles for that, right? It has to be assistive, real-time intent detection using natural language processing. I want to assist you, so I have to understand what you need. I'm the solution. You will tell me through voice or through click or whatever, what you need. I have to understand the intent. You may say it in different ways. For example, you are a doctor, you want to create a note for a patient. You can say create a note. You can say create a note for John Doe. You can say create a progress note for John Doe. You can say a lot of things in different ways. I have to understand the intent and I have to help you do that, right? So we need a streaming intent model, right? One that responds quickly and can understand the intent and take some action based on it, right? And it has to be invisible. So it means it has to have an immersive interface. What does that mean, immersive interface, right? It's a marketing term. But what it means is you don't have to, as the user of the product, make context switches. For you, everything flows smoothly in and out, right? You don't, oh, for this, I have to click on this tab and this button and this link and then it will work. That's not the kind of transition we want you to make. We want it to be very intuitive. That doesn't mean everything will be single page, but you know, there is a balance. So we need interleaved modes between dictation and commands, right? You can, the point of being assistive is that you can command the solution to do something. Hey, go create a note for me. You're issuing a command, right? And when you are issuing a command, so it will create a note, and then you are doing medical dictation also, which is the fundamental problem we are trying to solve, right? And context awareness. The product has to be aware of the context in which you are operating. Which patient are you seeing? Are you following up or are you creating a fresh note? Is the patient revisiting from a previous note? If so, what is the history? All this context has to be understood.
Even you have to give a set of commands, right? The voice cannot be recognized. Predefined commands has to be recognized, or maybe the word. Are you going to list out these are the commands you are going to
You have to. Okay, but at this point, when we are discussing architecture, we don't go into that detail of feature. But yes, what your point is
You
right.
have,
Yeah. So this is the typical architecture by Google. If you go to Google, there's a link anyway. This is what Google proposes as the bare minimum architecture you need for a live speech transcription system. If you want to build a live, and they are pioneers in that. They have the best live speech transcription system. Everybody can attest that. If not, you can go and see the performance numbers also. They are everywhere available. But they prescribe a three major component based system: ingester, transcriber, and reviewer. Ingester is basically somebody, so you learned about the event driven thing, right? Ingester is your producer, it produces the audio. Transcriber is your consumer, it will take the audio and convert to text, okay? Using ASRs, but let's, for the purpose of a discussion, let's assume that's magic. They will use some magic and they'll convert it to text. Reviewer is the part of the product that will display that. Displaying is not trivial problem in speech to text, right? Because you're speaking in real time. The audios are bytes coming to you in real time. You are translating that into text. You might want to go back and correct it. And so the display has to handle. You might send duplicates. You might say, hey, I think you said this word. But then 10 seconds later you might say, oh no wait, I now have better context. I think you said this. So you can make corrections, and most ASR are designed this way. Google itself has something called a stable text or stability ratio. With every text it sends, it gives you a stability ratio. If it is more than 90%, you can assume that Google won't change it again. It's final. But if it's less, that means Google is still processing and it might improve that text in the next millisecond or so. Right? This is a typical architecture. Everybody who builds a speech transcription system more or less follows it. But we need something more. Right? We need a voice agent in our product. Why? Because we've promised our users an immersive interface. Right? We said you don't have to context switch. So who will do the context switch? Somebody has to do that context switch, right? Now let's assume you are a doctor. We'll go back to the same use. Doctor, patient walks in, you say, hey, Suki, create a note. And then Suki brings up a note and you have to go and dictate something, right? Patient walked in, this is the symptom and all that. You do that dictation, that's medical dictation, that's speech to text. But you, at the same time, you can also issue a command. For example, patient walks in and say, hey, patient is a 51-year-old male, he has history of diabetes. At this point, as a doctor, you want to insert a lab report on diabetes. So you say, Suki, insert previous lab reports. And the lab reports are inserted, and you continue dictating. So you make switch between dictating and issuing some commands to the agent, and we don't want you to click for this, you continue talking. Right? We are understanding that you issued a command and we're dealing with it. Right? And at the end of the day, everything appears in order. It's not like when you said a command and we serve it after the entire dictation is done. No, it's chronologically ordered. Right? So we need a voice agent who can do that. Because we take that complexity on ourselves. We don't let users, because that's our promise in the mission. Now, note representation and EHR packet. One of the most significant challenges of a doctor in US healthcare is they have to learn different portals for EHR. Right? What if there is an agnostic portal? A note is a note is a note. You open a note, it has sections, you dictate. You don't care about how your specific EHR portal maps that note. Right? For example, when we talk about health record system, people have proprietary systems. Some systems, they take the note and they put all the text in one section. That's their representation. Some people have a separate section for diagnosis, separate section for history, separate section for something else, follow-up, prescription, medicines, whatnot, right? But doctor doesn't have to worry about that. They get to structure it the way they like. Either in one section or split section, it's up to you. As a doctor, you choose what's best for you. And then we will take the job of converting it into the EHR specific representation. You make the doctor's job easier, because that's what we promised. Right? And then natural language processing based command engine. Right? Because this requires intent detection. When you say something as a command, see, that could be infinite variety, right? Today we have so many commands. We have 50 plus commands, but you could add more. You may want, tomorrow we have so many feature requests, doctors coming in saying, hey, can you add this command? Can you add that command? Can you add this command, specific version of existing command? So people will always bring in diversity as they use the product. And that's good, that's organic growth of the product.
Let's
And
say
but you want but you want the natural language engine to understand that intent and cope up with it. Yeah, sorry.
The quick question. Let's say you add commands which is existing, whatever. COVID was evolved in 2019.
Same.
How will they understand which department I shall go?
Yeah. So when we add in, so we have a recursive solution for that. We have a command which says, Suki, what can I say? So if you don't know anything, you come in and you say, Suki, what can I say? It will show you what are the commands that you can use. So if we added something for COVID, it will be there in that list. So you can use it. So what I'm trying to say is the NLP engine that we're building is flexible. You can add more commands and there is an easy way to learn what I can do with the product. Right? But on top of these three pillars, these three are central pillars. You need something for audit engine because healthcare is heavily regulated. Right? We have to be HIPAA compliant, there have to be records and all that. So you need a good audit engine which can also manage licensing and metrics. Right? You need an extensibility manager, right? Because the use case diversity is huge, basically infinite. Because when you give a voice agent like Alexa or OK Google, right? You obviously when you start to use it, you want it to do more things. Like recently ChatGPT came out and when we all used that and we were like, hey, why doesn't Alexa do it? Why can't I talk like this with Alexa? Right? I mean, obviously when you give something that's so intuitive, people want it to do more. And that's why you need a good extensibility manager, which can extend your use cases without slowing you down. So these are the architectural components we needed in addition to Google's typical architecture. Right? Because what Google proposes is bread and butter. It's the basic part of everything. But then you need something more on top of it because you're building a product for a real market. It's not a theoretical academic project. Right? So this is Suki interface and I mentioned this because, not to, I mean obviously it'd be great if you can all experience the product, but just to get the idea of what I'll talk in next slides, this is the interface. We have a mobile app for Android and iOS. We have a website and then we also have a Windows app and a Mac app. We also have the ability to pair these things. If you have Suki on mobile and Suki on Windows, you can pair these things. But that's a whole separate class of problems. Maybe I'll talk in the next session. Yeah.
One of the typical problems with the audio-based system or voice-based system is you lose the flexibility to go back, for example, to navigate a typical IVR. How do you solve that for the voice system?
Can I take that next time? I'll remember your question. If I forget, please remind me. But because I want to cover it under the cycle, right? So this is a typical user flow in Suki, right? And I think this will probably answer your question. I'll check back with you after the slide. So you are a doctor, you come, you open a note, Suki, create a follow-up note for John Doe in case the text is not visible. And these text within angular brackets is what we call as slots or parameters. What that means is the John Doe can be anything. It could be Badri, it could be anybody. So any patient name, right? And similarly, follow-up note is the type of a note. You can give any type of note. There is a clinical note, diagnosis note, follow-up note, progress note, blah blah blah, anything. Right? And then you dictate, right? Patient is a 51-year-old, you dictate medical text, the actual documentation. Now it is 10 times faster because you are not typing. You are not worrying about where to click. You just open, you dictate, right? And then you get assistance, right? Suki will help you actually do something, right? Suki, insert a physical exam. You don't have, so a typical physical exam, if you haven't seen, has at least 8 to 10 parameters. Eyes, nose, lungs, chest, kidney, liver, everything, right? Most of the time, most patients have a normal physical exam or it differs by 1 or 2 category, right? But a doctor who is doing a note has to type all 10 lines for everybody if they are not using. What if you could just create a shorthand and then say, hey, insert a normal physical exam, I'll modify whatever is not applicable, but give me the basic text. Okay, so this is just one example of the command that helps the doctor. There are many more, right? Suki, show me vitals. If you want to just see what are the patient's vitals, most recent vitals. And in US, all of these are digitized, documented. So when you issue a command, show me vitals, boom, it shows you pop-up and there are vitals. What is the pulse, saturation, heartbeat, whatever, blood group, blah, blah, blah. All vitals. Yes. Then you have review and correct. So you've done a note and you want to change a few things there. There are avenues to do that. There is obviously the undo command, which is the most brute force. We can simply undo what you have done. right? Or you can say delete last sentence, delete last word, delete something. So we have few, not everything that we want to correct is a voice command today, but we are building them one by one as users request. But these exist today. You can say Suki change lung exam to shows no abnormalities. You inserted a normal physical exam, now you want to change only lung portion. So you can say Suki change X to Y and it will do that. So review and correct is also voice assist based, right? And all of these are captured in notes, right? And then send to EHR. You can say Suki submit a note. Hands free. All this time you're not typing a thing, not clicking anywhere. You just tap and open Suki, that's all. After that, it all went into autopilot, right? And while this is happening in the user flow, what's happening on the architecture, on the back end? Voice agent gets ready when you say this. So this is your typical state transition diagram. If you haven't learned about it, then it's the most handy tool you can get as an architect. Always remember state transition. The voice agent gets ready. It's ready to listen. It's ready to react. And then you go into a dictation mode. It's aware of the context. It knows you are in dictation. So it can do medical dictation. And it listens to both dictation and command. So there is parallelization. You are speaking and that's all one audio stream. But in that one audio stream, you are saying hypochondria also, you are saying Suki insert lab report also. The voice agent can distinguish between two. How? Based on the wake word Suki, right? Suki wake word like Alexa or OK Google. There is a wake word that tells, hey, now I am giving you a command, right? And there is a moderately complex state transition diagram that executes inside of that. But that's, if you're interested, I can talk about it. But that's what happened. So you came here, you're context aware, you're dictating, now you issued a command, we inserted a lab report, and then you end the command. Your intent is identified, it's served, it's accurate. And then you submit the code. So while you are doing your flow, the backend architecture is taking care of context, parallelization, dealing with audio, and ensuring everything happens in real time. So we spoke about real-time systems, right? Any real-time system always needs to respond below a second. Actually 500 milliseconds is the cutoff. And if you go by Spotify, it's 200 milliseconds. So anything that is greater than 200 milliseconds, human ear eyes can recognize that it's not instantaneous. So you have hard restriction on something being real time. So this is what is happening behind the flow. Yeah.
You have some escape patterns as well. For example, the name of a patient to be Suki.
Sorry.
Do you have some in typical programming paradigm, you have escape patterns, right?
Yeah. So any ASRs that you use, they are aware of this problem. And so they give you two APIs. Hints, you can provide ASR hints and bias them towards one word or another. Vocabulary, you can give them a dedicated set of vocabulary and they will treat those words as special words. So we do this real time. When you are a user, you log in, you have a dedicated set of hints because of your accent, because of the words you commonly use, because of the way these words are commonly transcribed by the ASRs. We have this data set. We send it to ASR as soon as you log in. So the ASR is ready for you. It's primed to listen to you, not general user. Okay?
Then how do you train the model for accents?
Yeah. So the flip answer to that is not my problem, ASR's problem. But all voice modulations, right? They follow an encoding pattern, and then they have a sampling pattern, right? Sampling rate. So when any ASR says that in order for us to accurately transcribe what you say, you have to send the samples in this rate. You have to use this encoding, right? That, to a great extent, nullifies the impact of accent and background noise, right? But in addition to that, you have resampling. Sometimes some people speak very fast, right? And people who get habituated to the product, they know it so well, they speak so fast, it's even hard for me, the human ear, to understand. But the ASR can understand it because that's resampled. So there are ways in computational linguistics and in speech processing in which the effect of accent is reduced. It can never be nullified. The effect of accent is always there, but it's reduced to an extent that it's practically negligible. But that's an interesting problem in ASR, automatic speech recognition systems. And that's like a whole big area in itself. Oh, I already came with this. Okay. So, what kind of scale are we dealing with, right? As an architect, you would like to know, you designed a system, you designed a state transition, wow, it looks nice on paper, but can it stand the test of time, right? So, you have, so let's, just to give you an idea, if you do a 10-minute dictation, if you speak for 10 minutes, and if you assume a 100 millisecond sample, right? So, whatever you're speaking for 10 minutes, every 100 millisecond we are creating one audio packet. Each packet is 4 KB in size, right? Okay? So that means for a 10-minute dictation, you get 6,000 packets. Each packet 4 KB, 24 MB of data. To support 100 concurrent users, I am not talking about millions and billions, okay? 100 concurrent users. If you are serving 100 users, you are processing 2.4 GB of data in 10 minutes, right? So if 100 users are using your product, you are processing 2.4 GB of data. This is, so before you go to big billion days, you first understand the primary scale that you are dealing with and how we can solve this problem. You can always extrapolate. So part of my job is just running benchmarks, right? Because every idea I come up with as an architect, I have to benchmark it. Can it handle the scale? If I want to use Redis, if I want to use GCP, if I want to use Kafka, if I want to use something else, I have to benchmark it. I have to really understand if it can tolerate my use case load, right? It can tolerate great load, but there will always be conditions attached. Okay, so people will say that, hey, if you use it in cluster mode, and if you have a 3-node cluster, each cluster has 16 GB RAM, then it can handle 250 million. Right? There will be conditions attached. So you have to figure out your conditions. What is my use case as an architect? So this is important. This requires groundwork. You will not get it on Google or anywhere. And then you have 200 to 400 writes per second on the node. Why so much? Because everything that you say, you remember that Google's architecture, there is a reviewer component which is displaying the text, is being written to a node, right? So everything you say, and ASRs don't have the concept of sentence or, I mean, they do give you sentence properly, but they are sending, you are speaking to them in audio, and they're sending you text back in real time. One word, one character, two characters, 2 words, half a sentence. So there are multiple writes that are happening, right? Anything can crash when that is happening. Any network can get disconnected. You have to account for all of that, right? So when you have such high concurrency and you are doing 200 to 400 writes per second, depends on the ASR, right? How quickly the ASR can respond. There are some ASRs that are slower. Google is actually usually the fastest. So you have to determine that. And then you have your inter-service latency cannot be 100 to 200 milliseconds. Let's say you are a fan of microservice architecture and you have like 25, 30 microservices. But just to go from A, B, C, D, E, come back to E, D, E, back to get back the response or finish it or whatever, that cannot be more than few hundred milliseconds, right? Because that's the major hop that you are taking in your product. So as an architectural restriction, this is what you have to remember, because you have to finish everything by the second. So this is the most slowest component. Network calls are probably the slowest component. And I'm assuming you have written a program that just shines, right? That's a big assumption, but I'm just saying that when we're evaluating, you can do that. You should take this into account. And then you have intra-service performance of microservice. So your own service, when it does internal logic computation, cannot be exceeding microservice. So if you have a programming language that you have written in, or if you have written code in such a way that it takes few milliseconds or 100 milliseconds to just finish something computing then and there, you have a problem in such a scenario. In some other product it may not be, but when you are dealing with real-time voice transcription, it's a problem. So you have to be sensitive to that. And this limits your choice of programming language, your stack. Your design has a lot of restrictions. Your design can't have superfluous things. You need to be very intelligent about what you do. Right? And new data keeps coming from EHR at few thousand records, probably taking a very conservative estimate. It's more than that. New appointments are getting created, patients are getting added, reports are getting generated, labs are being populated. All this is happening. So you have to consume them, stay up to date. Right? So there are high number of updates. Right? And then you have to use a POPs-up mechanism or an event broker mechanism, that deals with this asynchronously. and even potentially cache it, because you can't keep going to database every single time. You have hard restrictions on that. So this is the kind of scale you have to deal with, right? As when you are, so the topic is architecting the voice agent, and I'm just taking you from top to bottom. What was the problem? What was the mission? What was the architectural choices that we make, and do those choices support this kind of scale? This is a very basic scale. I mean, as the product grows, we are at probably a little bit more than this. We are probably 2x, 3x times more than this, but this is a very basic scale that you have to address to even prove that you can build a voice agent, right? So this is what we have. And the main challenges and approaches that we had, right? Interleaved command and dictation. As I told you, we don't want doctors to change context because they're very busy, they have to talk to patients. So we take up that. And so they may say a command when they are actually dictating medical text. You have to handle it. So that's the main challenge here. And minimize trips for data retrieval. There's a lot of data you have to retrieve, right? X-ray reports, lab results, appointments that the patients make which are stored in EHR. Whatever, there's so much of ecosystem outside of your product. You have to retrieve it and be up to date. And so you can't just keep going and you can't just say, hey, you know what, I don't have vitals, let me go and get it. It'll take 5 minutes and then you relax. You can't say like that. You have to be quick on your feet because a command can come anytime. The moment you're logged in, you can say any command. You can say show lab reports and it should be there, right? And then this is the approach. These are the approaches you take. Obviously, this is at a very high level. Obviously, I can't go too deep into them. But this is just to communicate the kind of approach we took to solving problems for the voice agent capabilities. And that is 2 modes to be maintained in the backend: command and dictation. I think this is no-brainer. When you design a system that can context switch, you have to treat each of those contexts as first-class citizens. There is a command mode in which it will work, and there is command plus dictation or dictation mode where the product will work. And that's what we design. These are first-class citizens. So when you log in, the entire product goes into that mode, right? First of all, there is voice mode. Like some doctors may choose not to use voice. They are habituated to clicking and tapping. So that's fine. You can switch off the badge. But if you switch on the badge, we are listening. And when we are listening, we are either in command mode or command plus dictation mode. So that is context awareness. So we design these modes as the first-class citizens in our component. We are either in this mode or that mode, and there's a big state transition that's happening based on the context. And switch modes based on the wake word Suki. And that's also the reason why we chose the word Suki. Because before this is an interesting trivia, the company was called Robin, right? And Robin was wake word. But when you say Robin, the ASRs can give different words. It's a word that can be easily, mistaken by ASRs. You need something unique, and that's why you have Alexa, OK Google, Cortana, because they have a certain pitch and tone, which is impossible to confuse with other words. That's why we went with Suki, because it gives us a good rate of accuracy in terms of detection, right? And so that's why it's wake word based detection, and we use ASRs that are specially trained to recognize the wake word. Because if you don't recognize the wake word, you can't give a command. Your product's context switching is based on wake word, so you have to be very sensitive about it and very accurate about it. You say in 100 different ways, you say Suki in different accents, I should be able to recognize. So I should be able to bias it. Then define command boundary. When do you end the command, right? Some of our commands have 12 words in them. Send Suki, set a reminder tomorrow for so and so event, for so and so person on so and so day, and keep it recurring for so and so. The command goes on forever, right? The diversity in command is huge. So you have to set a command boundary. The agent has to, voice agent has to act under certain guidelines. It has to choose a policy to terminate the command. It could be based on number of words. It could be based on the recognition of intent. Like, do you have enough data to recognize the intent? Then stop. Then process the intent. Don't keep waiting. So defining command boundary is itself a challenge, right? Parallelize command and transcription handling of audio. Inter-thread communication. This imposes between the voice agent, the command, and the dictation processor. So you learned that we made command and dictation first-class citizens. Now there is a processor which processes commands, and there is a processor which processes dictation, and there is a father of these two, voice agent, which handles both. You have to make sure they all communicate properly in real time, right? There's a lot of inter-thread communications, and your skills of all the concurrency classes you have taken on Udemy are put to test. And you should use queues and buffering to avoid data loss. You can't lose data. You can't lose an audio packet because the text will go vary. You can't lose text because nobody will use the product. So you have to ensure that in case of any failure, you are ready to respond, right? So you have to use these tactics. And then there should be information storage hierarchy. What about the information that is used in medium to long term, right? Like lab reports, patient data and all that. You're not going to cache it immediately, but you may need them quickly as and when required, whenever there is a command. So you have a tiered mechanism for them, right? And you use a criteria to put the data into tiers. And what that means is that let's say you are the user of the Suki, right? And you're using a typical node that I talked about in the cycle flow slide here, right? You're doing this typical flow. You're coming here, opening a node, doing some dictation, using a command, and handling, and doing that. And then, so what happens is that let's assume there are 100 patients. You can't get everybody's data and keep it in memory ready, right? Most of it has to stay in the database, which is a long-term storage or whatever. Some of it has to come to cache, okay? That can be decided on any criteria. Your cache addiction criteria, your cache policy are subjective to the product, but some of it has to come to cache, right? And the heuristics we use is, obviously you have an LRU policy or something like that, which you can cache, but we are also using based on how frequently this user accesses this patient's data. So there are custom heuristics you have to institute to make sure your cache is hot when the information is required. But then there is another level of tier, which is in memory. So you have a microservice, it has some memory, make use of it. Don't always make a trip to the cache, because even that will take few milliseconds. So if you do it in memory, it is wicked fast, it's a microsecond. So the logged in user, the user who is logged in, we know they need some data, right? So you get it from cache and you keep it in memory. So this is not a very new concept that we're doing. What I'm trying to say is when you use a tiered storage, information storage concept, you have to apply your business rules on top of it. You can't just say LRU or you can't just say something. You have to be intelligent about it and cache it or store it in such a way that satisfies your business case well. Optimize for what you are doing and don't just apply what you've learned of cache. So these are some of the techniques we use, right? And we have an app, it's on Play Store and all that. We can get you onboarded, but you can just try it and see, and you will experience. So with this, so you learned high-level stuff about the voice agent architecture, right? You can go and try the app, and you will see how many things are happening in the background, right? When you speak, when you give a command, when you're dictating a medical text and switching to command and coming back to medical text, there are so many things happening in parallel. Right? And this is what it takes to architect a voice agent. And this is all stemming from our problem statement. What you wanted to do, and you took some goals on yourself, and you told your engineering lead or whoever that, hey, I want a solution that caters to these principles, go build it. And you make architectural choices, and you build the design on top of it. So whatever you have learned today about access of variation or choosing the right database and event broker, you can apply all this and build an architecture. So treat this as a case study of how to actually go about fine-tuning the concepts that you have learned to a specific use case, in this case the voice agent, right? So I guess that's what I had. There is obviously, this is a very 30,000, 50,000 feet level talk. Each one of these is a separate component which has its own complexities. And there are a couple of problems that I haven't spoken about. The bridging problem is a major problem. How do you speak in one device and the text goes in some other device? Right? You are a doctor who's speaking in California, whatever you speak appears on the screen on a Windows machine that is in Bangalore. That bridging problem is itself a great problem, right? And that's another thing that we solve. We also have a platform problem, right? Naveen was talking about the talk, referred to the talk he made about platform. All these use cases that you have learned, or you have understood, or you have become aware of, multiply them 10x in complexity and diversity, and you have a use case for platform. When you're dealing with platform, just about anybody can come with any request, and you have to, when you say I'm building a platform or I'm publishing a platform, you have to address this, right? Kafka or somebody, so they cannot say, hey, my platform doesn't address this. They can't say that, because as a platform, there's something called as platform guarantee. Platform guarantees you certain basic functionality will always exist. That makes sense. So we have a platform problem also, because we are trying to build a speech processing platform for the entire healthcare domain, right? So that's a class of problems that I haven't talked about today. So I hope you got some lessons or some quick tips from this presentation. Thank you. Anand told me there's a lot of chocolate, so anybody who says anything gets chocolate.
Yes.
Doesn't have to be even a question.
Okay.
So one question, some of the conversation will be in the context of, say, X-ray or some other physical thing. How do you correlate that? If it's just a voice command, X-ray, particular part of the X-ray is something that you're talking about. So it is always contextual, right?
Yes.
How do you bring that in?
So that's a good question. Actually, let me start by saying we haven't solved that problem entirely.
Sir, what is the question?
So yeah, let me repeat that. So his question is, and let me know if I'm paraphrasing it incorrectly. X-ray or any medical data that you come up with is very context heavy. So how do you understand that if I want to see a portion of X-ray or an aspect of X-ray report, how do I issue a command to go into that? And how you can be context sensitive? Is that right? Okay. So one approach we are taking to that is any artifact that you get into a node gets defined by its boundaries, right? So we haven't dealt with images, but if it's text, like an X-ray report, that's an inference or a text or an observation with a conclusion, then, and that comes into the node, it has its defined boundary, right? And EHRs and US healthcare infrastructure have helped us because they have a standardized API called as FHIR. Okay, I don't remember the acronym or how it expands, but it has FHIR on HL7, so it's called as FHIR on HL7. That actually tries to conceptualize the clinical boundaries. What is an X-ray report? What is an observation? What is an instance of an X-ray report? What is the value? What is the deviation? What is the grade? All these are standardized. And when you retrieve this data from EHRs, these boundaries are marked in that data. So that helps us draw contextual boundaries in the data. Now, images are a different problem because images you can't have such standards in images because X-ray images are not it's very difficult to standardize X-ray images. But yes, you can. Solving images is a different problem which we are trying to tackle. But as long as it is textual information, the standardization APIs and the fact that we have an ASR engine that can parse and understand the information allows us to draw some contextual boundaries. I hope that answers. Thanks.
The ASR engine, is it something you have developed or you have taken it from open source or something?
Both, hybrid. So as I said, right, we need specialized ASR handling. There is no one, like you don't have a one sorting algorithm for everything. You don't have one ASR that can do everything properly. There are ASRs that are very good with medical dictation, but they don't do so well on normal English. But then there are ASRs that do very well on normal English and so on medical dictation. And then we also felt the need to develop an ASR that is tuned to what Suki users require. Because Suki has a user base and they are slightly different from other users. Right? They use spoken punctuation also, like they use comma, period and everything when they are doing reports. And there are certain characteristics that sets them apart from general users. So we use a combination of ASR, and that is where it gets a bit complicated. Because now you are sending the same audio stream to 3 different people, you're getting the text back and you're deciding which one to pick based on all those metrics. So that, and all this has to happen in real time. Nobody's waiting for you. You don't get time to do this. So that is why the stack is complicated. We use this because you don't have a single ASR that can solve the problem. At least as far as we know from the survey we have done, the benchmarks we have done, the reports we have done, nobody can solve this problem, common English plus medical dictation, using just one AS language. So we use a combination as of now. But yeah, we do have our own homegrown ASR, which we also use. I think it's in beta. It will probably go soon live on a wide basis. But we use a combination technique. I think, yeah.
And I have a general question because this is an architecture form, right?
Sure.
This, right, it is, this kind of approach is not specific to this domain, but can be applied to any domain I realize now. For example, in banks, if you have a trading application or something, right? Voice as an interface can become something big. For example, in my own company, for data visualization, they are developing products where for visually impaired, data can be audible in various ways,
Yeah.
kind of music, kind of thing, right?
Yeah.
So, is such kind of trend setting in for creating application interfaces more on audio based, more on text based, or voice based?
Yeah. I see. It's the same trend that I think. Again, this is take it with a pinch of salt. I have not done a market survey. It's the same thing that you observe with chatbots. Right? Initially, few people used it. They were not so accurate. Now they have become much smarter. And now most businesses try to use a chatbot, either in WhatsApp or on their own site. It's the same with voice. Initially, it was not so accurate, and it was like, okay, it's hit and miss. But then they became more and more intelligent. They allowed, fine tuning. Google can even do, handle so many languages. It can detect currency, it can detect dates, and so much, right? Because there's progress happening in that field, with especially after 2000. I think after 2017, 18, when I think transformers were introduced in machine learning. It's in the field. But so to come back to your question, right, it is becoming a general thing, and that is why I'm almost tempted not to talk about it. But since you pitched on it, the voice agent that we worked on, right? We took a lot of time to develop it. There is an ask to make it a platform. Like, I want this capability in my product. I want it to distinguish between what I say and just translate it versus do something, do an action. This I want as a generic feature in mind. We have people who ask for it, and we are trying to make it generic thing. Not just in our app, but for something.
Maybe APIs to voice commands.
Exactly. Yes. Come up with SDKs and deal with because this whole thing is built on gRPC. Our stack is mostly on gRPC as a network protocol. You typically require some clients to talk to us, right? We're also thinking about WebSockets, but then so there is an ask. So people want it, and they want to use. They want us to expose this functionality so that they can use it to be context sensitive. And we already have few customers in US who already do it, but we're trying to make it generic so that any health platform or anybody for that matter can use it.
Just to add on to what you said, I think so there are other companies who are solving that thing. There's a company by the name Slang Labs, based out of Bangalore. They are solving this. This is very, very context sensitive. For example, you have like probably 100 odd Indian languages. The way you speak, the dialect. There are Southeast Asian languages where the same word, but if you say it maybe a lot more ko or kho, so the meaning changes, right? So, but there are companies that are trying to solve it as a problem. For example, Slang Labs have integrated with Big Basket and a bunch of others in multiple Indian languages.
Yeah.
So if they have a level of accuracy.
And we want to do it for healthcare. We have set ourselves the mission to solve this problem for healthcare. Yeah.
So as I was a patient, usually doctors, I don't know how much they are compact, so, let's say morning till evening they might be having 10 patients or more, minimum I'm telling you. What they spare is hardly a few minutes, Is there any feature like which enhances more time to interact with this through this your app or by chance? The problem is to get another appointment, it will be big headache. Another 5 days, 10 days, something like that.
See, the two ways to answer this.
Yeah.
Suki, people who have tried Suki have reported. It's on our homepage, suki.ai. If you go, you will see that white paper, metric, everything. They've reported a 72% reduction in their documentation time. Okay, so they were spending, I showed you the chart, 1 to 2 hours extra per day. On an average, okay, some people spend more. They have reported 72% or 80% less in that. So they are spending maybe 15 minutes, 20 minutes, that's all. Okay, now if the doctor gets 1 hour 40 minutes extra, don't you think that will benefit all the patient? Because today he's spending 6 minutes per, if you take 2 hours as the benchmark, he's spending 6 minutes, and on an average they see 20 patients per day, right? There's some see more, but depends on specialty, whether a physician or a cardiologist, but something more. Let's take 20. You're spending 6 minutes per patient extra. Now that, it may seem like pennies and pence, right? But this all adds up. For a year, that becomes an entire month of doctor's time just doing notes in front of a web page. It's not what they're supposed to, they're not data entry operators, right? So if you give that time back to doctors, then obviously that will get distributed into two things, right? Either they will focus on more on patient care, they'll see more patients, or they'll relax and come back with higher productivity next day. So they can see, because if you are continuously burning out, they are also human, they can't treat, they keep treating patients like this. So I can talk, but it's better if you see the video. We have a nice video on our homepage where our doctor has actually spoken about how Suki has impacted their life. Okay, how she has saved time and all. It's a beautiful video, 7-minute video, you can watch it. And the second thing about that is, obviously, see, as a product, you can offer some value. We say, it reduces your clinical documentation. Now, what do you want to do with that time is up to you. If doctor chooses to spend time with their family, then that's not something we can dictate, right? And we can manage appointments. So using Suki, you can manage your appointments. You can figure out how many patients you are seeing today, whom you can set reminders, follow up. Suki will remind you. It will fetch all the. It makes your job easy and allows you to see more patients. So that's the product value.
Third thing is, if I want to, after the appointment, I come out of it, I want to have a quick question, quick answer. For that, I need to another appointment. That's a foolish thing. That was hell-like for me.
Yeah.
That is where I didn't find it very interactive with the doctor.
Yes.
Yeah, that's a question.
I agree. There are pain problems. I'm not saying Suki will solve everything, but it provides some value. So how that value is utilized is up to the doctors. Yeah.
So I have one curiosity. Can it be integrated with home assistant devices, or the ASR will come into play? Differences?
Yeah, agreed. So the question is, can this be integrated with home assistant devices? Not as of today. Today we have Boxer solution, the assistant app that you have on the phone, the website, and the app on the Windows and Mac. We are coming up with a platform. So when we come up with a platform, you get a URL. You can hit it. Anybody can hit it. You can hit it. Alexa can hit it. Somebody else can hit it. And then it will be available wherever you want it to be available. It can be on your smartwatch, whatever that can support speech or tap or whatever. It will be available there. But yeah, that's the mission. That's where we are going. Now we realize that this use case is more pervasive than we thought. So we are investing in making it more generic and available to every review.
How do you track the accuracy? Like you spoke about the review and the audit part, right?
Right.
How do you track and improvise over a period of time?
Oh, okay. So we should finish with this question. We have time for one more. Okay. So the question is, how do you improve from the review and corrections that we make? So I think it's very easy to answer in one way and very difficult in another. The easy answer is the machine learning model, right? Anything you correct is an input to the machine learning model that it was wrong. Now there is a body of research that tells corrections can be made because there is nothing inherently wrong with what was said, but the doctors want to enhance the meaning of what was said. So there is a paper published that talks about clinical significance. Okay, the term is clinical significance. You look for Google, you will get it. So there are 14 categories under which that clinical significance. So 14 categories of mistakes that voice assistants can do that are classified as clinically significant or not. Like spelling corrections, that doesn't matter, are clinically insignificant. It's okay. Maybe the models can assign less weight to that. But if you change the name of a medicine, right, and in medical field you all know the name of the tablets and prescriptions are dangerously close. You change one I, one C and it becomes a totally different drug altogether, right? Medical errors are a very big problem. So that is recognized as clinically significant. So you have a model that understands the corrections made and tries to understand the weightage of it based on clinical significance, right? But we haven't incorporated clinical significance yet Because as a concept, it is still waiting for vetting. I mean, it needs to be vetted. Whether 14 categories are enough or we need more, less, whatever. But the way the model improves is by understanding the corrections and trying to be sensitive to the context. So you're saying a word, then you say a line, then an entire paragraph. When you say an entire paragraph, the model has more information. It can understand what you say, the diseases, the symptoms, the text, and then it can try to be smarter the next time. So that's how we try to improve. And there is also a hybrid approach, like there is also manual input that goes. That there are certain set of experts who tell this should have been this, and the model did not spell that word because it doesn't understand medicine industry. So I am telling you change it, and that's another way we also improve. We have Suki experts panel who give us suggestions time to time by trying, and they're all doctors.
So today the doctor at the end of the transcription reviews it before the doctor says submit.
No. That option is available. So it comes in two modes. You have an enhanced review mode where you can say and a medical scribe will review it. Or you can have an automated mode where you say if you're satisfied with the app's performance, you don't want an additional review. And we have a good split. I mean, not many users use enhanced review because our transcriptions are quite accurate. Okay, so that's us. Suki, you can connect with me on LinkedIn. Would love to talk more offline and hope we meet up on multiple avenues. Good luck to the Meetup team. It was a pleasure being here. Thank you.